Hey, good afternoon, lads and ladies. Welcome back to MAC1140 Pre-Calculus. This is our last meeting before exam 2. So today I intend to do a handful of things. I'd like to work at least one more example of the problems like we saw last time, where we're solving a somewhat complicated inequality. Give us an opportunity to talk about that in a little more depth. And I'm also going to introduce the material to which we'll be moving after the test. Time is so short, this class has so much. I cannot sacrifice a day just saying, oh, well, you've got a test coming up, some new material. I'll let you know when we're switching to the stuff that is not on exam 2, but it should also be fairly obvious. Alrighty then, here we go. I'd also be happy to take a couple of homework questions. Let's lay out the plan first. So this is MAC1140, which is of course pre-calc. It's a lecture. And today is the 22nd of July, 2021. Today we're going to do maybe more quality or rational inequalities. Maybe some homework questions. And then we're going to introduce the next topic, which is exponential functions. So just like how we kind of move very fast through the section on quadratics, we're going to move very fast through the section on exponentials. They are hugely important, but also I know that they're a part of at least one class before this. And I don't want to be hyper redundant. We've got some dope shit to get to after them. So I'm going to move quickly. I'll say this, the study of exponentials is quickly preceded by the study of logarithms. I know it's possible to kind of creep through college algebra without really getting logarithms. No mas. You gotta understand those things to get through this class, I promise you. But with that said, let's take a look at one more example problem here. And while I'm queuing that up, you guys can maybe look at your homework and see if there are any questions you want to tackle in class from that. Please no quiz questions. So the quiz is intended to prepare you in a sense for the test. I want you working through those on your own. Okay. Not like that. Why does that say chapter 3 test? This must be a review. Okay. So we can come back to this guy. Let's solve the inequality x plus 2 over x plus 3 is strictly less than, let's do less than or equal to x minus 1 over x minus 2. So certainly this is a rational inequality. It's an inequality, and the objects involved are rational functions. But we're not in a position to solve it yet. And I'd like you guys to tell me what to do. So what's my first step?
Factor.
Before we, there's one
Get
thing.
everything to one side.
Yeah. So remember, factoring is the first step for graphing a rational function. But here we're looking at that other sequence of steps for solving inequalities. And yeah, my first step is to pull everything to one side. I need a 0 on one or the other sides to follow that procedure. So I'm going to subtract this whole term over here. That'll give me x plus 2 over x plus 3 minus x minus 1 over x minus 2 is less than or equal to 0. Okay, what should I do now?
Combine the terms.
Good. So remember, what we need is like a single rational function on one side and 0 on the other side. So before I can apply that method, I need to glue these guys together into a single fraction. And that means I need to have a common denominator. So this piece his denominator is x plus 3. If I want him to have the same denominator as this guy, I need to give him the missing factor of x minus 2. In other words, I'm going to write these both as fractions whose denominator is x plus 3 times x minus 2. So I'll just go ahead and put those denominators here. X plus 3 times x minus 2. Hey, kitty, you can't be up here. This is Nala Cat. She's decided to get in the way. Hey, sweetie. Yeah. Say hello to the class. Yes, you're beautiful, but you're gonna move.
She looks just like my kitty. She's only 5 months though.
Oh, yeah, we got her 2.5 years ago, something like that. And she was a little kitten back then. She's very sweet. Black cats are the best. All right. So this guy, x plus 2 over x plus 3, he still has the x plus 2 upstairs. But he was missing the x minus 2 factor downstairs. So if I'm going to write him with the denominator x plus 3 times x minus 2, he needs to get that factor downstairs and upstairs. And you see, I could cancel these and I'd go right back to what we had. But I'm not going to do that because my goal is to put them together. Same thing over here, the x minus 1 factor is still there, but he needed the x plus 3 factor. So I got to add that, multiply by that upstairs and downstairs. Now that these have the same denominator, I can put them into a single fraction. So that would be x plus 2 times x minus 2 minus x minus 1 times x plus 3 all over that common denominator of x plus 3 times x minus 2. And this is less than or equal to 0. Now I need to kind of FOIL these out, distribute my minus sign, and then I can factor the top. So this is x squared minus 4 minus, I'll put it all in parentheses, minus x squared plus 2x minus 3. That's all over x plus 3 times x minus 2, and that's all still less than or equal to 0. So if I distribute the negative and combine like terms, I'll have x squared minus x squared. So the x squareds will go. I don't have any x's here, but I have a minus 2x here. So this is going to be minus 2x. And then I've got a minus 4 and a plus 3. So it's going to be minus 1. And then my downstairs is still x plus 3, x minus 2. And all of this is still less than or equal to 0. All right. So we pulled everything to one side, had a common denominator. I distributed this negative and combined like terms. That gets us to here. And now this is the sort of thing we know how to handle. So normally we'd say factor top and bottom. The bottom's already factored. The top is linear. It doesn't need to be factored. So what do I do from here?
Do you find your roots now?
Yeah, the roots and vertical asymptotes, right? I need to find the places where I can change sign. You can call those something if you want, special numbers, magic numbers. I used to call them critical numbers, but that term is used for something specific in calculus, so I don't want to mislead you. Vertical asymptotes are at x equals 2 from this guy and negative 3 from this guy. And upstairs, my roots or root, what value of x will make the top 0?
Negative 1/2.
Yeah, very good. If I set negative 2x minus 1 equal to 0, that's the same as saying negative 2x equals 1. So x is negative 1/2. Okay, so these are all the places where this function can change sign, go from being negative to positive or positive to negative. What do I do with these three numbers now that I have them?
Number line?
Very good. So these guys go on a number line. I'll space them out, somewhat evenly, even though they're not actually evenly spaced. This -3, this -0.5, and this +2. And that chops my number line up into several regions. And remember, the big deal here is that in each of these regions, this inequality will either be true or not true, right? This function here will either be positive or negative. Can't change sign anywhere else. Now, we're again in that case where the horizontal asymptote is y equals 0, right? Because the bottom is degree 2, the top is degree 1. So I can't sneak my way through with end behavior. I do need to actually test a point. A little bit of advice, test a point from a region that's really easy to work with. Like in here, 0 is there. So I can test x equals 0 in that region. If you plug 0 into this inequality, the top is -1, and the bottom is 3 times -2. So this would be -1 over +3 times -2 is less than or equal to 0. And that's the same as saying -1 over -6. Less than or equal to 0, which is the same as saying +1/6 is less than or equal to 0. Or you can just look at the left-hand side, I guess, because we're doing the sign thing. So when you plug 0 in to this left-hand side, you get +1/6. In other words, we're positive in this region. Is everybody comfy with that?
Yeah.
Right. So we had to figure out what's going on in one of these regions, and I could test a point from every single region if I wanted to, but I'm way too lazy for that. Who can tell me, does a plus or a minus go here and why?
Minus,
Very good, it's a minus, and why is that?
because the degree is an odd number.
Good. Yeah, the multiplicity of this factor right here, the x minus 2 factor, which is where that 2 on my number line came from, the multiplicity of that factor is 1. It's an odd multiplicity, so we'll change sign as we hop over him. In fact, these are all odd multiplicity. These are all multiplicity 1 factors. So we're going to change sign as we hop over each. And now that my number line is complete, I can write down my solution. The solution to this inequality is the same as the solution to this inequality. That's what all of these double arrows mean, if and only if. I mean, they have the exact same solution sets. So my original inequality is true if and only if this last inequality is true. This last inequality is true provided this thing is less than 0, less than or equal to 0. And this number line gives me the sign of this function. So less than or equal to 0, that means I'm looking for the minus regions. My solution set in interval notation would be -3 to -1/2 union width 2 to infinity. And then because it's a less than or equal to, I need to be careful with my parens or brackets. Right? If a number makes this equal to 0, that's okay. I include that. Use a bracket. If a number makes that undefined, then I wouldn't use that bracket. So tell me first, over here with the 3, paren or bracket?
Parenthesis.
Parentheses, right? Because if you plug -3 into this apparatus, that makes the bottom 0. That makes this factor here 0. So the inequality would be undefined. -1/2, paren or bracket?
Bracket.
Very good, bracket. -1/2 makes the top 0. If the top is 0, then the whole thing is 0. If the whole thing is 0, then this is a true statement. 0 is less than or equal to 0. And then the 2, just like the -3, gets a paren because he makes the bottom 0. So that's our solution set. All right, you're gonna have to do this on the test. You're gonna have to do this on the test. And I need to see the steps. If you give me the answer without the work, 2 out of 10, and that's if the answer is perfect. So please, questions?
So you want us to do the line graph and everything?
Yeah, so if I give you an inequality, a rational or polynomial inequality, I will need you to go through all these steps, getting it into this form, finding the numbers where you can change sign, the roots or VAs, making the number line, filling out the signs, and then writing down the answer in interval notation. Each one of these steps I would need to see to get full credit.
Okay, cool beans.
We have an opportunity to connect this back to something from earlier in the semester. So I'm going to do one more example that does that. And then I see Austin asked to see number 24, presumably homework 5, Austin?
I think it's homework 6.
Homework 6, okay, the new one. All right, so we'll do that after this one more example. The thing to which we can connect is domains, right? We can now take this skill and revisit the concept of a domain, because a lot of the domain questions, specifically with square roots, require solving inequalities. Give me one moment. Alrighty, sorry about that, guys. So yeah, domains. We can connect this back to the domain finding problem from before. That was the place where we encountered nonlinear inequalities for the first time. So I want to find the domain. What would be fun? How about yeah, why not? What the fuck? Let's just practice some other stuff too. This guy. This is going to let me do two things, actually. So we're going to find the domain. We're going to solve an inequality. That's what's necessary in order to find the domain. And along the way, we're going to see one factoring trick that I haven't had a chance to show you guys yet. And that's a little substitution trick. So let's go ahead and talk about what's necessary to find the domain here. What sort of red flags do I have?
The radical in the denominator.
Good. Yeah. I think we kind of nailed both things there. The red flags. I've got variables under an even root. Variables under a square root. So I'm going to need the thing under the square root to be greater than or equal to 0. All right, we need the stuff under the radical to not be negative. And the other thing is we've got variables downstairs, variables in the denominator. So I need the whole thing, the downstairs here, square root of x to the 4 minus 5x squared plus 4. I need that apparatus to not be 0. Now, this thing not being 0, together with this thing needing to be greater than or equal to 0, we can say together, these require, let's think about it. This thing would be 0 if and only if the thing under the square root is 0. And the thing under the square root is this. So I can say, kind of put these two conditions together and say that what I'm really needing here is x to the 4 minus 5x squared plus 4 to be strictly greater than 0. If that radical wasn't downstairs, then I would just solve the greater than or equal to inequality. But if this thing is equal to 0, then the whole downstairs would be 0, and I can't have that. So kind of putting these two red flags together, we can knock them both out at once by just solving this inequality. Any questions about that step there? It's a bit of a logic leap. Okay. Now, everything in this inequality is a polynomial inequality. Everything has already been pulled to one side. So my first step would be to factor. Does anybody know how to factor something like this? It's a degree 4 polynomial.
You can do the AC method, but like
So
but
remember,
have like x squared instead
yeah,
of just an
that's
x.
the game. Yep. So normally the AC method is just for quadratics, but we're lucky here in that the only powers of x are even powers. So you can kind of think of this as x squared squared minus 5x squared plus 4 is greater than 0. And some people like to write some other symbol. I'll say z equals x squared, so they can just focus on thinking of it as a quadratic. The other option is to use the rational roots theorem. That'll work fine. You don't need to make any, this is called a substitution. You don't need to make a substitution if you want to dive in with your rational roots theorem, but there are some problems that you can solve through substitutions like this for which the rational roots theorem won't work. Maybe the roots aren't rational. So to proceed from here, we use the AC method, right? A is 1, C is 4, B is -5. So I need two numbers that multiply to 4 and sum to -5. Those would be -4 and -1. So this factors as z minus 4 times z minus 1 is strictly greater than 0, i.e., now I'll go back and put my x squared back in. This is x squared minus 4 times x squared minus 1 is strictly greater than 0. And we can factor further. X squared minus 4 is x minus 2 times x plus 2. X squared minus 1 is x minus 1 times x plus 1. That's our difference of squares. That trick is that a squared minus b squared can always be written as a minus b times a plus b. And now we're fully factored. So my roots for VAs, there are no VAs here, but the roots are -2, -1, +1, +2. So those are the special numbers that go on my number line. Quite a few of them, so -2, +2. Okay. Who can help me out? Who can help me fill in one of these signs without any test points?
If it's x to the 4th, wouldn't the leftmost be up? Like, so positive?
Good, because this is 1 times x to the 4. our lead coefficient is positive and our degree is even, we know that actually both of the outermost ones are positive. Comes from the end behavior. As x goes to negative infinity, y goes to positive infinity, and as x goes to positive infinity, y goes to positive infinity. So kind of each of these are telling me these guys. And now I can use my multiplicity trick to fill in the rest. These are all multiplicity 1 factors. So we change here, we change here, we change here, and we change here. And you can kind of think of that as a way to check your work. All right. Questions so far?
Could you do that end behavior trick with the other question? Like the previous one?
No. Yeah, good question. So the last one, you can use tricks like that for rational functions. The end behavior here, though, is as x goes to negative infinity, y goes to 0. And as x goes to positive infinity, y goes to 0, because y equals 0 is the horizontal asymptote. So if you have a horizontal asymptote like 2 or 5 or something like that, something positive, then you could say, ah, yeah, it's got to be positive on both sides, both far ends. But 0 is neither positive nor negative. So this is the kind of one case where you can't use the end behavior to help. So with a rational function, the end behavior is the horizontal asymptote. Remember what end behavior means? It's just what does the function do as x gets really, really large. For a polynomial, that means, how do the arrows point? Are they up, down, or what? For a rational function, that means what's the horizontal asymptote? And if your horizontal asymptote is anything other than 0, then you can take the sign of the horizontal asymptote to be the sign in both of these outermost regions. But here, because the horizontal asymptote is 0, and 0 is neither negative nor positive, we can't use that. But in some cases, we could.
Got it.
Good question. All right. So we're almost done. The solution to this inequality is then going to be open intervals, because it's strictly greater than. Having this thing equal to 0 would make the downstairs of my function 0, which is no good. So I'm just going to take the open intervals with the plus. So my domain is the solution to that inequality. Is the interval from negative infinity to -2, union with the interval from -1 to 1, union with the intervals from 2 to infinity, all open. Not so bad, right? And you see how much this multiplicity trick speeds things up. Back when we first learned about nonlinear inequalities was when we were talking about domains. And back then, when you filled out your number line, you had to test a point from each region. It was a pain in the ass. Now that you know about multiplicities, you can do things so much faster. Yeah, it's good stuff.
And why are all those parentheses? Can you explain that again?
So what happens if I plug, say, +1 into this inequality? Well, then this factor right here would be 0, which is going to make this whole thing 0. And 0 is not strictly greater than 0. So we're looking for a strict inequality. We're saying, where is this thing absolutely bigger than 0? Not equal to 0, but strictly bigger than 0. At any one of these numbers, that object, this polynomial, is exactly equal to 0. And since 0 is not strictly bigger than 0, those are not a part of the solution. Another way to think of it is, if you plug any of those numbers into this function, 1, -1, 2, -2, downstairs here, you'll get 0. And I can't have 0 in the downstairs of a fraction. So kind of comes back to how these two connected together to give me this inequality. Good questions. All right. Anything else we'd like to ask or say about this before we move on? Okay, then. The only homework question I got was homework 6, problem 24 from Austin. If you have another one that you'd like to see, now is a good time to take a peek and let me know what that is or those are. What was it, 24? Okay, so find the common factors top to bottom, find intercepts and asymptotes, any if something doesn't exist, and then we're going to draw the graph. So they've told us that there may be factors which are common to the top and bottom. That's sweet of them to do. I'll write this down. Number 24. Here is x cubed minus 2x squared minus 3x. Downstairs is x minus 3. Factor. Find intercepts. Features. And graph. All right. So let's begin by factoring. The first thing I see when I look at that numerator is that every term has an x. So I can factor out an x, and what's left would then be x squared minus 2x minus 3. And then the quadratic that's left over, x squared minus 2x minus 3, I can factor that as x minus 3 times x plus 1. So the top is x times x minus 3 times x plus 1. And the bottom is still just x minus 3, which I'll remind you is the same as x minus 3 in parentheses times 1. So there is indeed a common factor. It's the x minus 3. You strike that, but only if x is not equal to 3. And it's important that you make note of this. So in other words, I can cancel a factor top to bottom as long as that factor isn't 0. Right? 0 over 0 is not 1. 0 over 0 is undefined. In calculus, I'll show you ways to look at 0 over 0. Turns out could be anything. But as long as x is not 3, this factor is not 0, and you can cancel any non-zero factor top to bottom, which means r of x is equal to x times x plus 1, or all x different from 3. What feature should I expect to see on the graph when x is equal to 3?
A circle?
A hole?
Something, yeah, a hole or a circle, a little missing point. Normally we would think that this factor would give us a vertical asymptote, right? Because it's downstairs, and when it's 0, that usually gives a VA. But because it cancels, it's like it might as well have not been there. It's like someone just foolishly wrote this function in this much more complicated form. But the x minus 3 factor does do something. It produces a hole. It alters the domain. We're taking this to be the definition of the function r. And you can't plug 3 into this. You plug 3 into this, the bottom 0. That's not okay. So this function r is equal to x times x plus 1, but with the one exception that at x equals 3, this thing is undefined. So if I'm talking about r, I can say everywhere except for 3, it looks like this, but at 3, it's undefined, or 3 is not in the domain. So intercepts. X-intercepts come from this thing being equal to 0, right? And it's much easier to work with this form. So that's going to happen when x is equal to 0 and when x is equal to -1, i.e. we've got the following points, 0, 0, and -1, 0 for our x-intercepts. Y-intercept, we always find that by plugging in x equals 0. So here r of 0, again, easier to work with this form. It's 0 times 0 plus 1, which is 0. So the y-intercept, we actually already had it. It's also an x-intercept. No asymptotes, right? Because the degree of the top, sorry, no horizontal asymptote because the degree of the top is bigger than the degree of the bottom. No vertical asymptotes because in the factored form, factored simplified form, the bottom is never equal to 0. There's nothing I can plug into this to make the bottom 0. There is no bottom. The bottom is just 1. So these are all the features we normally care about. We know that there's going to be a hole at x equals 3. We don't know the y value of that hole yet, but I'm going to show you how to make this go. So you just draw the graph. Right? Here's the function whose form is easiest to graph. The form in which the function is easiest to graph is this simplified form. And that's a quadratic, x times x plus 1. You know, you've got x-intercepts at 0, 0, and I'll call this over here -1. It's x squared plus x. The lead coefficient is positive, so we're going to open up. So we're going to something like this. But then somewhere way over here, when x is equal to 3, that's a bad picture, isn't it? There's a hole here. And if you want to know the y value of that hole, you can find it by plugging 3 into this guy. That'll be 3 times 4 is 12. That's all. Oops, sorry, what's going on? All right, yeah, that's it. That's the game, right? So you graph a rational function like this that has a common factor top to bottom. That's why our first step is always to factor the top and the bottom. You cancel the factor, then just graph the cleaned up version. But remember that canceled factor tells you there's a hole somewhere.
The other part of it was find the domain and range, and I struggled with finding the range on this one.
Okay, so our domain is going to be all numbers except for 3, right? And if you think about just the rational function in this form, you can see that the domain all real numbers except x equals 3. In interval notation, that's negative infinity to 3, union with 3 to infinity. And remember, if you're having trouble seeing that, I strongly encourage you to draw a number line. Interval notation does take a little bit of practice, but you see over here, everything up to 3, that's this guy. Everything bigger than 3, that's this guy. And it's not the same as negative infinity to 2 union with 4 to infinity. Those are very different animals because there's lots and lots of numbers between 2 and 3 and between 3 and 4. So that's our domain. The range here could be tricky, but in this case it's not. Let me draw a slightly better graph for you. That will help with the range. Put a little more love into that graph. Draw the hole, which I know is at 3,12 first. I know my x-intercepts are here and here. That points maybe. It's not perfect, but it works. Here's our graph. Like I said, the domain we already know. You can play the squishing game, right? The smooshing game. Smoosh everything down onto the x-axis for the domain. The only thing that doesn't get hit when you play that smooshing game is 3. 1, 2, 3. Because if you smoosh everything down onto the x-axis, this hole lands on 3. But the range is going to be from whatever this y value is up to infinity. So we need to find this y value down here. Who can help me find this y value down here? What is it we're really looking for?
The vertex.
Right. And you might ask, doesn't the hole affect the range? Who can answer that for me? Does this hole mean 12 isn't going to be in the range? Or does the hole have any effect on the range?
No.
It doesn't have any effect because it's an open circle.
Yes and no. So correct, no effect. But it's not necessarily that it's an open circle. If I cover up this piece and ask you, does the circle affect the range? The answer would be yes. If there wasn't anything under my hand, if that was the whole graph, then the range would be missing the number 12. But because of the symmetry, right, even though there's a point missing here, so there's a y value that would be missing from the range here, the symmetric point over here is going to land on 12. So again, you think of the smooshing game. If I smoosh just this piece onto the y-axis, I would get, everything from here up except for 12. But then when I smoosh this piece onto the y-axis, and remember that's what we got to do. We got to smoosh everything onto the y-axis. Whatever got missed from this hole when I smoosh this over will get hit by this. So to find my range, I already know what the form of the range is going to be. It's going to be bracket something up to positive infinity. That's the orange shaded region here. The question is, what's this guy? And the answer, somebody said it a second ago, is it's the y value of the vertex. So you've got multiple options to find that. I'm going to do it by completing the square. So we know r of x is equal to x times x plus 1 for all x not equal to 3. That's the same as x squared plus x this time. So somebody help me out. What's my first step in completing the square here to put this into the vertex form where I can find h and k? Somebody help me complete the square here.
Take the magic number.
Good. And how do I find that number?
It would be the b term over 2 squared.
Very good. So I'm going to add and subtract my magic number. Before Twitter, we called these pound signs. They stood for the word number. Here, b is 1, right? 1x squared is a is 1 plus bx is 1x. So this is 1/2 all squared, which is 1/4. So I write this as x squared plus x plus 1/4 minus 1/4. And now I need to factor the first 3 terms. And remember, there's a trick to this. You can use the AC method, but if you're having a hard time seeing how this factors, remember that the inside here is kind of always the trick. So it's going to be x minus 1/2, or sorry, x plus 1/2 all squared. And you can verify that. If you FOIL this out, you get x times x is x squared plus 1/2 x plus 1/2 x, which is 1x, plus 1/2 squared, which is 1/4. And then the minus 1/4 is still chilling right here. So h, so the vertex, is the point h comma k. What is h? What's the x value of that vertex? You can see from the graph, it should be negative, right? It's the x value right here.
Negative 1/2.
Excellent, right? This piece, specifically this piece, tells you the x value of the vertex. This is x minus negative 1/2. And k, what is the y value of my vertex?
1/4.
Almost. So remember, the vertex form is a times x minus h squared plus k. So this one has a negative built in, but this one doesn't. So there is a 1/4, but it's negative. In other words, this point right here, my vertex is negative 1/2 comma negative 1/4. So my range, negative 1/4 to infinity. Is that the only way to do it? No. Is it the best way to do it? Yeah. All right, so completing the square, this is one of the skills that we're meant to practice in this class. We want to come out of this class comfortable completing the square. You will need it multiple places in Calc 1 and Calc 2. So I need you to learn it. It will be on the test. Is there anything else from this question? I think Austin was the one who asked it, so I'll give Austin a chance first. Is there anything else from this question we wanted to look at, Austin?
No, I think I'm good.
Okay, does anybody else see anything here that they'd like to look at a little more closely? Okay then. And that means we're ready to introduce the new material. The new material, this is where things What I'm about to say is not going to be on exam 2. It will be on exam 3, but not on exam 2. So this is the start of exponential functions. So this is not on exam 2. Exponential functions are called exponential because the variable is in a new place, the exponent. Now, your book says that an exponential function is one of the form f of x equals a to the x. I think they're missing out on a bunch of notation options here. Why not use b? Because we call this word the base, or we call this symbol here the base. But the big deal is that the variable x is in the power now, and we haven't seen that anywhere in the semester, right? Polynomials, power functions, rational functions, they all have powers of x, right? Like x squared, x cubed, x to the 1/2, stuff like that. But they never have a power that is x. So this is new. This is entirely new, and it's going to give us completely different graph shapes, lots of new behavior terminology. These things do have asymptotes. They've got lots of cool features. But before I get there, I'd say, or more generally, something like c times a to the x. So oftentimes you'll have a number out front here. Your book doesn't include that in the definition, but myself, all mathematicians would say something like this is still an exponential function. All right, the number a here is called the base. It has to be positive. And we like a to be different from 1, because otherwise this is boring. Right, 1 to the x is not going to do anything special. Let's just start with an example. Let's see if we can sketch f of x equals 2 to the x by plotting points. So because the variable is now in the exponent, all of your algebra rules for exponents are going to be really important in this section. I'm going to sort of subtly review those as we go through here. We're going to plot points, which means we're going to make a table. And let's just try -3, -2, -1, 0, 1, 2, and 3. Okay. If I plug in -1 for x here, f of -3, -3 for x here, what is f of -3? Well, it's going to be 2 to the -3, but nobody wants to call it that. How do I write this more nicely? What's the rule?
1/2 to the third.
Very good. So this is the same as having 1/2 cubed, and 2 cubed is 8. So this is 1/8. And the rule there is that a to the -b is the same as 1/a to the +b. Right, so a negative power is like a reciprocal, but you got to remember where all the pieces go. It's not the same as like a to the 1/b. That's like a root. That would be very different. All right, with that in mind, 2 to the -2, that's 1/2 squared. That's 1/4. 2 to the -1, that's 1/2. 2 to the 0, what's that?
1.
Yeah, good. 2 to the 0 is 1. And there's a rule here also. A to the 0 is always equal to 1 for any number A, with one exception. What number can I not raise to the 0 nicely?
Zero.
Yeah, good, right? So there's two rules that would kind of be in conflict there. Anything to the 0 is always supposed to be 1. But 0 raised to any power is always supposed to be 0. So what is 0 to the 0? It should be equal to 1 because it's something raised to the power 0. And this rule says anything raised to the power 0 is 1. But it should also be 0 because 0 raised to any power should be 0. 0 to the 0 is like 0 over 0. It doesn't have a fixed meaning. So it's called an indeterminate form. And you will study those in calculus. All right, the rest of these are easy. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. So we've got our table. Let's plot some points. I'm going to try to make the scale here somewhat even. The X and Y scale is about the same. So you can get a feel for just how quickly these functions grow. Let's call this 1, 2, 3, -1. Two, 3, 4, 5, 6, 7, 8. A little bit taller to get to 8. Okay, the reason I'm being so careful with my scales here is to make a point. Let's start plotting them. So this tells me that -3, 1/8 is on my graph. So when x is equal to -3, f of x is equal to positive 1/8. Positive 1/8, very, very small. Something like this. When x is equal to 2, y is equal to 1/4, which is twice as tall, but twice as tall as tiny is still tiny. When x is equal to -1, y is equal to 1/2. So, okay, getting there. When x is equal to 0, y is equal to positive 1. When x is equal to 1, y is equal to 2. Oh, I apologize, guys. My wife is calling. I need to answer this. I'm sorry. Okay, guys, sorry about that. Wife going to the doctor, left the baby here with me, needed to check up on things real quickly. We've plotted a bunch of points, but we haven't finished yet. We've plotted everything up to this row. 1, 2 was the last point we plotted. Our next point is 2, 4. Right here. And then the last point we have from our table is 3, 8, which is right here. So what does this curve look like? As we go further and further to the left over here, these points are going to get smaller and smaller. The next one would be at -4, 1/16. So you actually have an asymptote over here that this graph is going to approach and try to sit down on. It's y = 0. And then as we go over this way, this thing is exploding, but it doesn't have any vertical asymptotes. Here is a very nice graph of 2 to the x. And this is still just decreasing. I'm just having a hard time drawing. So still going down over here like this, just having a hard time drawing. And going up over here like this. So this is what 2 to the x looks like.
Professor,
Yes.
I don't know if with that's an exponential with exponential graphs and stuff, it slowly approaches 0, but does it ever approach 0? I just know that it takes forever to touch it.
So it will never touch the line
Okay.
y = 0. It sits down on there really hard, really fast. Like it goes towards 0 over this way, super duper fast, but it does never touch it. That's true. So we're going to make a list of observations about this graph in just a minute that'll apply to all exponentials. The first thing I want to point out is that this growth over here grows insanely fast. Every time we take a step to the right by 1 unit, this thing doubles in height, right? So like this point is twice as tall as this point. This point is twice as tall as this point. The next point, if you double the height, would be way over, where is it? So if I come over 1 more, and I double that height, the next point would be up here. And the one after that would be off the top of the page. So these grow much, much faster than any, what are called algebraic or polynomial functions. Much, much faster. It's a neat fact, and in Calc 1, you're going to learn about limits and rates of change in great detail. Exponential functions have a higher rate of change, meaning they grow faster than any other class of algebraic functions, meaning functions you can form out of like square roots, polynomials, rational functions, stuff like that. They grow very, very fast. Even if you think of how quick 1 over x like blows up as you get close to 0 from the right, this is the rate of change here will eventually exceed any of those per unit step. So what else do we notice about this guy? There's the observation, was it Erica who was asking about the horizontal asymptote over here? This HA, y = 0, we do have an asymptote. And it never touches that asymptote. So let me grab a fresh sheet of paper and we're going to write some observations. Graph somewhere we can see it. Rational functions, remember, they can touch their horizontal asymptotes. But exponential functions, let's say here, let's say it like this, facts about exponential functions. All right, so they grow very fast. And as you go off to the left here, they decay very fast also. So they grow and decay very quickly. They never touch their horizontal asymptote, which can also be said as, i.e., a to the x is never equal to 0. There's no real number x that makes this happen. So this is true for all real numbers x, so even complex numbers. What else do you notice about this graph? So it grows fast. It sits down on the line y equals 0, but it never touches it or crosses it. What else? Think increasing, decreasing. Do you see any interesting features of this guy relating to its increasing, decreasing behavior?
It's always increasing.
Mm-hmm. They're monotone. That's the term for that. There are some exponentials. So imagine you do a transformation of this. You flip the graph over like that. Then it would look like this. So that's always decreasing. So a function that's incapable of turning around either always goes up or always goes down. Those are called monotone functions. Mono for single, tone like tonic. They're always doing one thing. What else do we notice? Yes, another way you could say this, no x-intercepts, right?
You could also say, I know it's not like about the graph, it's more about the table, but the fractions are always going to be like the opposite. So it's going to be 8 when it's 2, 3, or 2, -3, it'll be 1, 8, 8.
Yeah, there's a certain symmetry to the algebra, isn't there? We're gonna hit that in just a second. So I won't list that specifically here, but yeah, 2 to the x and 2 to the negative x have a certain symmetry. What else? I think that's all the crucial stuff. The y-intercept, if you're just looking at something like a to the x, the y-intercept is always the point 0, 1. And for c times a to the x, it's always 0, c. For that reason, c is sometimes called the initial value or starting value for these functions. Yeah, that's it. So I'd like to take a look at just one other example, and then we will wrap up for the day because I don't want to give you too much to mess with. Obvious things we're going to do with these, we're going to graph all sorts of transformations of them. We're going to shift them up, down, left, right. We're going to flip them, stretch them, all that stuff. We're going to look at their rates of change. That's an important thing. It turns out the rate of change for an exponential is always proportional to the y value. So I'd like to graph 1/2 to the x next. Now there's a long way to do this and a short way to do this. The long way to do this is to repeat what we just did a second ago, make a big old table, plot the points. Anybody think of a faster way?
Could it have something to do with the, never mind.
I don't know, go ahead, go ahead. Even if it's wrong, it's okay. I'd love to hear what you have to say. That's how we learn. I can't tell you how many times I shouted out incorrect shit in class.
Well, I was just thinking of the parabola.
It's not directly connected to anything with parabolas because the power is the variable, but there is something connected to the graph we just looked at. Think about that algebra rule that you know, a to the negative b is 1 over a to the positive b. 1/2 is 2 to the negative 1, right?
Yes.
So forget about the x outside. 1/2, just the inside, is 2 to the negative 1. So 1/2 to the x is 2 to the negative 1 to the x. And then there's a neat rule. This is the same as 2 to the negative 1 times x, or just 2 to the negative x. So the algebra rule here, and this is one of the reasons I wanted to show it to you like this, the rule that's super useful here is that if you take one number and you raise that to another number, and then you raise that whole thing to a third number, this is the same as the first number raised to the product of the two numbers. And we're going to use this rule in sort of both directions, where you sort of factor the power and then bring one of those factors out, and also in the forward direction, like we used it here, where you've really got like 2 raised to something, all raised to something else. So it's from here to here that I use this rule. 2 to the negative 1, all to the x is 2 to the negative 1 times x. When we learn about logarithms, by the way, there will be a similar rule. All right. So f of x here, I can write this as 2 to the negative x. And this is a transformation of the graph we just looked at, 2 to the x. Specifically, what transformation? What do I have to do to this graph to get this graph?
Horizontal shift or flip?
Yeah, it's a horizontal scaling, particularly a
Scaling.
horizontal flip. Flip or reflection, it's about the y-axis. Spin it around horizontally. So we remember 2 to the x, it's like this. So 2 to the negative x is this flipped over. So I'll go ahead and draw it down here, and I'll draw it carefully with some points. That means, so what did I do? I had eight, 4, 2, and 1. So on the old graph, on 2 to the x, we had the point positive 3, comma 8. So when we flip that point over, it's going to become negative 3, comma 8. On the old graph, we had positive 2, comma 4. So on this flipped graph, we're going to have negative 2, comma 4. On the old graph, we had 1, comma 2. So now we're going to have negative 1, comma 2. 0, comma 1 doesn't change. 1, comma 1/2, 2, comma 1/4, and 3, comma 1/8. So what's this look like? As you get close to the horizontal asymptote, it becomes hard to draw because the graph gets so close to the x-axis My pen is too thick. This is what 1/2 to the x looks like. The horizontal asymptote is still y equals 0, but now I'm approaching it as we go off to the right. I guess that's another thing we can add to our list of features here, is that they only approach their horizontal asymptote on one side. All the rational functions we looked at with horizontal asymptotes, they went to the same thing on both sides. But exponentials only approach their asymptote on one side, either as you run off to the right or as you run off to the left, but not both. So this is it. This is the graph of 1/2 to the x, which is the same as 2 to the negative x. The ordered pairs here, -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. You get it as a transformation. Right? That's the slick thing. What do you notice about this function? It's always decreasing, right? Things that are different from the previous. That last one was always increasing, and it increased really fast. This one is always decreasing, and it decreases really fast. And that's what I meant when I said, that's why I said monotone back here. Either monotone, because they're not necessarily always increasing. The ones that increase are always increasing, and the ones that decrease are always decreasing. So the very last thing I'll say here f of x equals a to the x is an exponential, and I'll abbreviate exponential exp all the time, exponential growth function if the base a is bigger than 1. If you take a number bigger than 1 and you raise it to larger and larger powers, it gets bigger and bigger. And we call it an exponential decay function if a is between 0 and 1. Right, so if a is smaller than 1. So like here, 1/2, my base is 1/2, which is smaller than 1. So this is a decay function. And the other guy, my base was 2. 2 is bigger than 1. So that's a growth function. That's the basics of exponentials. There's lots of stuff that we're going to talk about. Compound interest, the number e, Euler's number, very special number. And then we're going to use these as our basis for talking about logarithms. So we're going to, the inverse of an exponential is a special function called a logarithm. They're hard to define. You can't define them using basic algebra. You have to define them as the inverse of an exponential or through some calculus tricks, but for us, definitely inverses of exponentials. Fun question before I let you go. So we're almost done. I'll let you go in a few seconds. Why does A need to be positive? Right, if A is equal to 1, then no matter what you plug in for X, you're always going to get 1. That's boring, right? That's not hard to figure out why we don't want A to be 1. Because 1 squared, 1 cubed, 1 to the 4, 1 to the 5, 1 to the -6, all of that shit would just be 1. It's a constant.
Is it because the exponent could be a fraction, and then if it's negative, you get a imaginary number?
Very good. So why do we care about the sign of A? Because yeah, if A is negative, say down here, in A to the X, we require A to be positive because otherwise the output could be very apologize for the pun, quite complex. Yeah, literally. For example, take,
Wouldn't it? Oh,
sorry, go ahead.
I was gonna say, wouldn't it be a little wonky because like you have to have like an even number in order for it to be positive, and an odd it'll be negative. So like it'll be very like up down type thing.
What Jada just said is absolutely correct, right? So if I take a to be a negative number, then when x is an even whole number, we'd be outputting positive values. And when x is an odd whole number, we'd be outputting negative values. And it gets even worse. It gets even worse than that because, like, I think it was Maxwell or Benjamin who said, well, what if I put in a fraction? So here I'm using -1 for a, and we'll just see what sort of bullshit we get. Like Jada says, we'll look at even and odd numbers. So if I plug in 1, I have -1 to the 1, that's -1. If I plug in 2, that's -1 to the 2, that's +1. If I plug in 3, -1 to the 3 is -1. Plug in 4, you get +1. So it'd be bouncing back and forth between positives and negatives. If I put in some shit like 1/2, -1 raised to the 1/2 power, well, that's the square root of -1. That's I. That's not even a real number. And if you really want to bake your noodle a little bit, try to think of like, what the fuck is -1 to the pi? Okay, I'll buy this shit. I can take -1 and multiply it by itself 1, 2, 3, or 4 times. That's easy. Raising it to the 1/2 power, it's a little bit weird, but okay, I know what complex numbers are, right? The square root of -1, that's I can handle that. But what the fuck would it even mean to raise -1 to the power of pi? Good answers to that question require something called complex analysis. So if you want to see answers to this stuff, it's a whole field of mathematics called complex analysis. And for number theorists, my field of mathematics that I study myself is called analytic number theory, partition combinatorics. Complex analysis plays a hugely important role. And that's where you instead of thinking of functions as stuff that like take in real numbers and spit out real numbers, so two-dimensional graphs, you think of functions as things that take in complex numbers and spit out complex numbers. So you have four-dimensional graphs. Those are hard to visualize, but some things are really, really nice. Like some stuff, when you choose to think of it in the complex plane, becomes a lot nicer than when you think of it about the real numbers. So I'll leave you with a cute little quote about complex analysis. This is from Paul Hadamard. He said that the shortest distance, or the shortest path between two, it's kind of a cute statement, it's not anything deep, between two true statements on the real line passes through the complex plane. Cute little quote. Of course, it's punny and it's stupid because, like, yeah, the shortest distance from 2 points on the plane on a line is going to be the straight line connecting them. How do you even have a statement live on the real line? It doesn't make sense. But in short, what he's saying here is that sometimes the easiest way to prove something about real numbers or functions of real numbers is to consider them instead as functions of a complex variable and work in that setting where your inputs and outputs are complex numbers. And it's a true statement, and when viewed in that way. There are lots of calculus problems, integrals specifically, come see me in Calc 2, lots of integrals that we just can't solve. Think about them in terms of real numbers, they're not just hard, they're impossible. But if you let me reconsider that function as a function of a complex variable and do the integral as a contour integral over the complex plane, boom, all of a sudden I got it for you, no problem. So sometimes backing up and looking at your seemingly simple problem as a piece of a bigger, more complicated problem can actually make life easier. And that's one of those big life lessons that kind of can be learned through mathematics. All right, that's all I've got for you guys. Exam is Monday. Exam covers primarily polynomials and rational functions, but of course it's everything that we haven't, or everything that we have done since exam 1. Remember inverse functions. I was very gentle on inverse functions on exam 1 because we hadn't had a lot of time to talk about them or digest them yet. I'm going to put some problems relating to inverse functions on exam 2, some tougher ones where you have to solve for an inverse, maybe tell me a little bit about restricting a domain to make a function one-to-one, that sort of thing. So everything from 2.8 up through, what is it, 3.6 through the end of chapter 3 is going to be on your exam 2. So that's 2.8 up through 3.7. If you have any questions, come see me in office hours, send me a Canvas message. If you're stuck on a homework problem, take a picture of your work, send it to me. I'll give you a nice deep reply. Otherwise, I will see you guys on Monday. If you have any special accommodations for the exam, just like before exam 1, please send me an email just to verify that everything's set up. That's it. Take care, guys.
I have a question.
Sure.
So you still haven't graded or regraded my worksheets or my test things?
I know,
was-
yeah, and I've got your
Okay.
emails. I'm just still stacked with other stuff, but I promise I will get it done.
Okay, got it. Just
That's
checking.
okay. I appreciate you bugging me. That's what it's gonna take.
Okay,
But yeah, it'll happen. I promise.
got
And
it.
you're open for office hours today. So
Yeah, normal office hour 3 to 4.
okay. All right. Cool beans.
All right, guys.